Okay, so the last topic is mechanisms of heat transfer. And this is, as much as I'd like to skip this, this is pretty important for 3D printing. This is how heat transfers between objects. So there's a couple ways. There's conduction, radiation, and convection. Under radiation, you could also add absorption, but the process is the same whether you're radiating or absorbing heat. Heat current is how we measure the rate of heat transfer. I don't know why this book doesn't use P, because this is power. Every other book I've seen uses P, but this book uses H. So to avoid confusion, I'm using H. But the units are watts, just because it's still power. And they call it heat current. So generally speaking, heat current is a time derivative of heat, but we're going to use more specifically equations that are specific to conduction, radiation, and convection. So first up is conduction. This is how thermal energy transfers through a material. So like when we talked about thermal isolation of the print head on a 3D printer, the tip is hot, the top is not. So generally speaking, you would have heat conduction from the tip to the back of it. So what are they doing to prevent that conduction from happening? So what's literally happening during conduction is the hotter side of the material has molecular vibrations that are faster than the cold side. Those vibrations start bumping into other molecules. Those vibrations transfer down the line until the molecules on the other side are vibrating at the same rate and thus as hot as the one side. So we describe one side as T hot and the other side is T cold. And the material has some thickness L and some cross-sectional area A. So those variables are going to be in our equation. So the heat current of conduction is Ka, T hot minus T cold over the length. K is a new variable called thermal conductivity, and that's just a property of the material that describes how quickly the heat is transferring from one side to another. It's got units of watts per meter times Kelvin. Again, A is cross-sectional area. This is the hot side, temperature of the hot side minus temperature of the cold side, and L is the thickness. Watts per meter times Kelvin, yeah. Okay. So thermal conductivity values can be found in table 17.5. All right. Thermal resistance, R value, anyone in here bought that big pink insulation for their house? It's rated based on the thickness, right? If it's thinner, it's like R15, the thicker stuff's R30. What is that R number? It's actually the thermal resistance. It's resisting temperature transfer through the material. Obviously, the thicker the material, it's going to be more resistive to heat transfer. L is the thickness. So if you've got, let's say this is your house. This is the walls of your house right here. And so you've got insulation in your house. Then L would be the thickness of that insulation. And this is the cold side in the winter. This is the hot side in your house. And then the cross-sectional area would be like the dimensions of this wall right here. Okay, so depending on what kind of insulation you have in here, you can have that blown-in insulation. You could have air, which would be a poor choice. You could stuff your walls with kittens, or you could buy the pink insulation. Then you would have a different K value for each of them, or if you want, you can calculate the thermal resistance, R, and the thermal resistance is the thickness over K, L over K. Okay, so R has SI units of square meters times Kelvin divided by watts. Times Kelvin divided by watts. It's got really funky units if you're in British imperial units. It's square feet times degrees Fahrenheit times hours per BTU.
Now why do they use Fahrenheit in that unit?
Oh, this is not SI. That's why. This is not SI. This is.
British imperial units isn't from Britain?
It's part of British imperial units, but we adopted it and then Britain ditched it. So the only people on the planet that use British imperial units is America. Yeah. I think there might be some territories that still use British imperial units. I'm not sure, but anyway, like maybe Jamaica, who knows, I don't know. But when you go to the, Home Depot or whatever, and you buy R30, that's 30 square feet degrees Fahrenheit times hours divided by BTU. So that's the units of the pink insulation you buy at the store. So that would just be a mean homework problem, but I could just have you convert. Like, what's R30 in SI units? I know. Now, you'll have the joy of doing the conversions, because I think one of the problems they give you something in BTU, so it's like, why? Okay, so our walls are not just pink insulation, because that would get pretty soggy in the winter, yeah? Our walls are made up of more than just the insulation. Our walls have sheetrock, drywall, wood, drywall, insulation, and then on the other side, you're going to have drywall and the inside of your house. So there's a lot of layers, and each layer is going to have its own K value. So every layer, you can have K1, K2, K3, K4, and they're all transferring heat through them. This is sort of a derivation. You know how sometimes they say, okay, yada, 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 this is the key take-home message. So this derivation says, all right, if you're going to calculate the conduction through this material, then you'd need to know Tx. That's the temperature at the interface. So for a T hot minus T cold, well, through this material, it's T hot minus Tx. And then through this material, it would be Tx minus T cold. All right, we don't really care what Tx is. We really just care about what's the whole conduction through both slabs, or all four slabs. So do your algebra, and then the x will go away, and this is the take-home equation here. The heat of conduction for multiple slabs is from one side through all the materials to the other side. That's T hot minus T cold. The surface area is the same for all the slabs, and then you divide it by the thickness over the K value. And this term, L over K, we just said was equal to our R value. So you could actually replace each of these fractions with R1 plus R2. And then if you've got more than 2, you can add it plus R3 plus R4. So this is for multiple slabs.
I just noticed is that this is the same as Ohm's law.
It's the same as Ohm's law.
Yeah, if H is your heat current, so electric current equals your hot minus cold is like your potential difference.
Yeah,
And then
divided by resistance.
It's the same principle.
So your area,
Wow, that's pretty cool.
times your variable or your difference in heat.
What's that?
So your area times your difference in heat would basically.
Your area times your difference in heat. That would be equivalent to potential.
Yeah.
Yeah. Maybe that's why they call it heat current. Probably, because someone out there is just as smart as Jordan. I'm not that smart. I'm pretty impressed. All right. I'm not saying that to be a jackass. That sounded very jackassy, but I meant that in all sincerity. I know. Well, I have to qualify it so the people on YouTube were like, burn! I'm like, no, not. I didn't mean it like that. So, okay. See, this is why I'm not a stand-up comedian. It's not smooth, right? I don't just lay the bombs and keep going. I'm like, wait, I have to explain my joke. Because I don't think everybody understood it. Well, at least I didn't understand it as it was coming out of my mouth, so.
Big hat.
All right, so there's your equation for actual useful applications. If you guys take, well, like I said, this is going to come up in your REE classes probably. I think for time we're going to have to skip examples, so you actually have some time to talk to your team. So we'll go ahead and skip the examples because the solutions are in your packet already. All right, so the next one is radiation. I'm going to go through these last ones fairly quickly because I think that the most important one for your life is the heat of conduction. This is the one you're going to see again. Well, I don't know if you'll even see this one on the final, but you will likely see this in another engineering class.
Oh, okay.
The other ones you might not ever see outside of physics. Depends on what you go into. So radiation, this is the exchange of heat with the environment by electromagnetic waves. So this is visible light, infrared light. This is how you get warmed by the sun. The sun provides light. Light actually heats us up, which is good. Otherwise, we would be dead. So this is different when we say radiation. This is different than nuclear radiation. So thermal radiation is not the same as nuclear radiation. This is false color infrared image to show this person has different temperature gradients across their body, and then the cold cola is obviously going to be a very different temperature.
So is the cap still on? Because you would think that his mouth would be a little bit cooler.
Yeah, I would think it would be a more interesting picture if it showed the cold cola going through. Yeah. It's just a stock photo. It's not actually drinking it. So this is the equation we use for the heat transfer due to radiation. It's this side of it. This symbol is lowercase sigma, E, A, T to the fourth. So sigma is Stefan-Boltzmann constant. So you've got this new constant with some really ugly units. E is not the electric charge of an electron. It's emissivity, and this is a property of a material measuring how much it radiates heat. So this is a value somewhere between 0 and 1. Typically, I think the book just says set it equal to 1. So I think that's not one that we usually worry about looking up in a table. So there's no units on emissivity. Temperature must be in Kelvin. This is the first time we haven't had a delta T in an equation, so you have to have this in Kelvin, otherwise it won't cancel with the units on the Stefan-Boltzmann constant. And this is the first time you've ever seen an equation that had a power to the fourth, which is unique to electromagnetic radiation. So we'll see that again in 223, but it's black body radiation. So anything else? Okay, there's an example, but it's a plug and chug example, so we don't need to do that in class. You can look at the example at home. You want this on the final? Yeah. It's a pretty easy one. You probably won't see this on the final. Yeah, it would make a good bonus problem because it's like solve for the heat conduction if you're given the area, you're given the emissivity, you're given the temperature. Plug and chug. Yes.
Maybe you can give it some really wacky units that we have to do some serious conversion.
Oh, yeah.
Yeah.
I could put the temperature in Fahrenheit, make you convert.
Yeah.
All right. So I said sort of associated with radiation is absorption. They're really the same equation. It's just radiation means an object is radiating heat. Absorption means it's absorbing heat. The mechanism's the same, so the equation's the same. In this case, the temperature is the temperature of the environment as opposed to the temperature of the object. Otherwise, there's nothing new here. Nothing to see here. Moving along. And the last one, I'll let you guys finish writing, but convection, there's no equation that just simply describes convection that is appropriate for this level, so I'm not going to list an equation for convection, but convection is one other method of heat transfer, and we can just observe what convection looks like. So this is where hotter materials will rise, colder materials sink, so when you're boiling water, you end up getting these circular, the cycling of the water as the hot water rises and the cold water sinks. This works in the air too, so you get convection currents in the air. That's how the birds of prey will glide around in a circle, because they're usually these big spiraling vents that go up and up and up and up and up in the sky. So the birds will just ride them up, and then they'll get out of the thermal vent and glide down, and that's really a bird just playing around with convection. So that's convection. That summarizes our mechanisms of heat transfer. So any final questions about the lecture?
There's no formula for convection?
There probably is, but there isn't one in our textbook, so my guess is that it's either overly complicated or too, I don't know. I don't know why what they do is they basically, I just don't really I don't like their approach. They have a way to calculate convection, but it's sort of the process of elimination, and they say, this is the heat current that it's getting from the stove, so you can calculate conduction from the stove, and you can calculate the heat loss due to radiation, and then you just take the difference and you say, well, the rest of it must be convection. And I said, well, that's kind of dumb, so I cut out all the problems that they had for convection, because I just thought it was kind of a weird way to do it. So, all right. So the rest of class is lab time, so you guys can be looking things up about 3D printers, picking out a topic to research for next week. I'll be sticking around to help you guys find stuff if you're not having much luck. So
I got my phone temperature already.
let me see if I had anything else. That's it. Cool. All right.